All right, hi guys, we're back with another lecture with this time starting on chapter 10 on Laplace transforms. Okay, this will be the last major topic we cover in the course, but it is a very important one, especially for engineering. Okay, so we'll start with the required skills like we normally do, and for this first section, we're going to do about 6 sections on these things. For this first section, the only required skill we actually have is integration. Okay, it's just the ability to actually integrate something. Integration by parts, basic integration, things like that. Okay, and even then, we'll develop some shortcuts for these Laplace transforms where that won't be necessary the entire time. Okay, so I want to cover what this is and our motivation for using it, but I'm going to give you the definition first, if only because I want to kind of work from that to sort of give an explanation for what exactly a Laplace transform is. So your book has a slightly more formal definition, but I'm just going to give you the formula here. And so if I have a function f of t, okay, so little f, okay, I'm going to define the Laplace transform of f, typically use a capital L. Your book uses a print L. I don't know. I was always taught to use a script L. It doesn't matter. Okay, so some capital L. So the Laplace transform of f of t. So Laplace transform of some function f of t. Okay. So this is equal to some function in S. Okay, so we're basically returning a function into another function with a different variable, right? So Laplace transform f of t is some function in S, and that function is defined by the following. It is the integral from 0 to infinity of e to the negative st times f of t dt. Okay? All right, so again, the result of this particular definite integral, it's improper, but it's a definite integral. The result of this particular definite integral, if it's integrable, is some function in S. That function we get for S, that is the Laplace transform of F. So how are these two things related? How is F and the Laplace transform of F, how are they related? Well, they're not really. I'll give you guys the analogy I typically use. When you were in high school, you learned a foreign language, right? You had to start taking classes in a foreign language. And let's say hypothetically you took German, right? And your very first year taking that foreign language, you didn't speak it very well, right? Yeah, I mean you're nowhere close to being fluent. You're just acquiring vocabulary. And I can already picture you guys in your very first test, right? Like the question is in German, right? So you read it, you're like, I have no idea what that means, right? But you read the question. In your head, you translate the question from German to English. Then you answer it in English in your head. And then you take that answer, translate it back into German, and then give that particular answer, right? Okay, that's not speaking German, yeah? That's what you did was you used English as this weird substitute in the middle for actually having this conversation, yes? What you did was you took something, you translated it into something that was more easily handled, then took the answer and translated that back. And in point of fact, this can be done in differential equations as well. Suppose I have some differential equation, let's say p of y. Well, I don't want to use any formal notation just yet. Okay, so let's say I have a differential equation. Okay, and it's got some terms, y double prime, y prime, etc. Right? Okay, so this is our differential equation. Now, we could just attempt to find a solution, right? So ideally, we just want to take all this crap, apply some sort of processes to it, and we come up with, well, y. We'll say y of t, right? That's what I want, right? I want to be able to solve for whatever this thing equals. Okay. here's what Laplace transforms do. Laplace transforms take this function, okay, this differential equation, right? And what they do is they translate it. So it's no longer in t, okay? All right, so I translate it into Laplace language, right? And so now I have an equation in y double prime of s, y prime of s, et cetera, right? All right. And due to some interesting structural rules with what happens here, I then solve, and what I get, of course, is whatever the Laplace transform of y is, okay? And I take this and I untranslate it, for lack of a better word, right? In the same way that you were asked a German question, asked for a German answer, and what you did was you translated it to English, solve it that way, and then translate it back into German. The same principle is happening here, right? I'm taking this function, translating it into just a different language, solving that instead, and then untranslating, right? This seems like more work, doesn't it? Right? I mean, it kind of seems like I took something which was fairly simple and direct, and I added a whole bunch of extra steps. So why would we ever want to do this? Well, if I'm being completely honest, for simple differential equations, it is more work to use Laplace transforms. Okay, it is more work to translate, solve, than untranslate than it is just to have done the damn thing to begin with. So why is this so interesting? Why is this so powerful and so common among engineers and physicists that we use it all the time? And it's not its effect on the basic nice functions that we normally deal with, the nice questions we deal with. Okay, it has to do with the requirements for this function, for this to work. Okay, for this to be even defined, this integral has to exist. Yes? Okay. Then I basically need one thing from this integral, right? I need it to be bounded, right? Yeah, I need one other thing, but I want to focus on the boundedness, right? I can't have this going infinite at a rate that can't be covered up by this. Does that make sense? Right? Yeah, I'm integrating over an infinitely long interval from 0 to infinity. So clearly, I need this term to go to 0. If this doesn't go to 0, you remember sequences and series, I know you do. If this term doesn't go to 0, well, then this thing won't have a definite integral. It'll be infinitely large. It doesn't make any sense, right? So I need it to be bounded, and I also just need it to be defined on the interval. Now, there's a reason that we say defined on the interval as opposed to continuous on the interval, because I don't mean continuous. As a quick example, we know in integrals, the geometric representation of a definite integral. Let's say I have a and b, and here's my integral. There's my curve, rather. I know that the integral here just represents the area underneath this curve between a and b. Yes? Okay, yeah. Okay. What if I was missing a point, right? What if I were missing that point? Yeah? Well, all I have to do is I have to just subtract off the area immediately below that point, yes? Well, yeah, but how wide is a point? Doesn't it have 0 width? Well, if that point has 0 width, then what I've just subtracted is 0 area, length times width, right? So I subtracted off no area. Well, it turns out then that the integral from a to b of this particular function, that value is actually independent from whether or not that single point actually exists. And so really, this is the same rule that we're using to integrate things that are, let's say, like this. Right? This isn't continuous, and yet I can still I can still comprehend what the integral here is by just taking the sum of these areas, right? Okay, so this is not continuous, but it is something called piecewise continuous. It turns out that all I need to make this work is that I need for f of t to be piecewise continuous, and that is fantastic, okay? The Laplace transforms are used in engineering and physics because they handle piecewise functions exceptionally well, right? Like really, really, really nicely, okay? All right, there's a formal definition for what piecewise continuous means. I'm going to give you the intuitive one. If you want the formal one, it's on page 6 something. Hell, I don't know. 673, okay? But the intuitive one is good enough for us. Quite literally, piecewise continuous means that it is composed of continuous pieces. That's it, right? Yeah. More specifically, I guess, if you want to be technical, over every finite-sized interval, it has to be composed of a finite number of continuous pieces. So I can't have, like, between 1 and 5, I can't have it make infinitely many continuous pieces between 1 to 5. Okay, but again, finitely many pieces is fine. Okay, which is what our piecewise functions look like, right? I mean, how many piecewise functions have you dealt with that have had more than 4, 5, 6 pieces? Okay. So how do I handle this thing? Well, I'm going to work one of these the long way. Now, unfortunately, this is another one of those skills like when you learn derivatives and integrals where you learn the limit definition of the derivative and you kind of struggle with that a bit. And then, of course, you were then taught the really, really short way to take derivatives. And the same thing with integrals, right? You were taught the limit definition of the integral, right? That like large, obnoxious thing involved an infinite sum. And then you were taught just, doing the opposite of differentiation. There's a shortcut for this. And in point of fact, I'm going to give that to you at the very end. I'm going to give you a table of Laplace transforms you are just going to have to learn. Okay? But I want to show you how this one works first and, of course, justify some things for how this thing works. And then, of course, demonstrate a few properties that we're going to use to more effectively be able to use our Laplace transforms. Okay, so I would like to do this function because this is overwhelmingly the function that we have seen most often this semester. I would like to know if f of t is equal to e to the at find the Laplace transform of f of t. So I want the Laplace transform of this. Now I stuck a in here because, again, I want this sort of definition to work for all exponential functions that we're going to look at, right? Okay, well, let's just put it into our definition, right? So I know the Laplace transform. I know the Laplace transform is, here we go, it's the integral from 0 to infinity of e to the negative st times e to the at dt. I just need to evaluate this integral. Okay, so how am I going to do that? So bear in mind, as far as this integral is concerned, a and s are not variables. Yes? A we know is a constant from here, and while s is technically a variable, our integral process is going to treat it as a constant, right? So the first thing I want to do is actually, I'd like to combine these two exponential terms. Okay, so I'm going to combine this as integral 0 to infinity as e. Okay, so when you multiply like bases, you add the exponents. That's negative st plus at, but I want to factor out the t because that's my only technical variable, right? And I'd also like to factor out the negative 1. So take a minute and convince yourself that this is equivalent to that, right? I would have had negative st plus at, factor out the t. That gives me negative s plus a times t, and then factor out the negative 1. I've got negative s minus a times t. Now remember, this is a constant, right? Negative s minus a, as far as this integral is concerned, is a constant, so I know how to integrate this. And it's an improper integral, so we're going to go ahead and look at a limit. Okay? So this is just the limit as, what do I want to use? Let's use k. as k approaches infinity of negative 1 over s minus a times e the negative s minus a t evaluated from 0 to k. Okay, again, I've got to rewrite my bounds. We're going to rewrite it as a limit because that's how we do improper integrals. And again, the integral of e to the bt is 1 over b e to the bt, right? Integral of e to the 4t is 1/4 e to the 4t. Same thing here. It's the reciprocal of this coefficient, negative 1 over s minus a times e to the negative s minus a t. Okay, so let's look at what we have. What I've got then is I need to plug in k, subtract from that, plugging in 0. Let's see what we get. The limit as k approaches infinity of negative 1 over s minus a times e to the negative s minus a times k minus negative 1 over s minus a times e to negative s minus a times 0. Again, plugging in k, 0 for t. Now, one of these terms is fairly simple. 0 times s minus a is 0. Doesn't matter what s minus a is. E to the 0 is 1. Negative, negative. This is just 1 over s minus a, right? This term's going to be fine. But again, remember what I said. I needed this integral actually to exist, right? Which means I need this value to be finite, which means I need this value, well, not to be infinite, okay? So as k approaches infinity, this term has no k's in it, but what about this one? Well, the only k is here. And we need to think about what happens when this k goes to infinity. As that k goes to infinity, what happens to this exponential term? Well, that depends. So I got two facts here. I know that the limit as n approaches infinity of e to the n, that's infinite. And I know that the limit as n approaches infinity of e to the negative n, I know that one's 0, right? So I know that s minus a times k is going to be infinitely large. The question is it going to be positive, which is divergent for us, or is it going to be negative, at which point in time this is 0 and everything's fine? I don't know. You see, this is negative, but I don't know what s minus a is because I don't know the value of s and I don't know the value of a, right? If s is larger than a, then this value will be positive. That's a negative number, a positive number, and k is positive. This will be negative. But if a is bigger than s, then this thing diverges and it's infinitely large, and all of a sudden our integral doesn't work. Well, since I'm arbitrarily defining s, I'm just going to put in a restriction here, right? I'm just going to put in a restriction right here, this one, comma. I'm going to say that s has to be larger than a, right? Again, listen, this Laplace transform is temporary, right? It doesn't mean anything. I'm just translating this for the purposes of working another problem, and then I'm going to untranslate it, yeah? So whatever restriction I have to put on s to make this thing work, it's fine, right? As long as there's some values for s for which this works, that's what we're going to do. So as long as I assume that s is bigger than a, then this is a negative infinitely large sum. E to the negative infinity there goes to 0. This is negative 1 over a. This whole term is 0, right? So this whole term goes to 0. So over here I get negative 1 over s minus a. I get 1 over s minus a. That's it. So the Laplace transform of e to the at for any value a, this is 1 over s minus a. Yeah. Now again, this is a lot of work, and honestly, the ones for cosine and sine are even longer than this, and the ones for products of exponential functions, and they're even longer. So we don't want to have to do this all the time, right? What I would like to do is I would like to just sort of memorize the easy formulas for Laplace transforms, the simple, the most commonly occurring formulas that we have, okay? So let me give you those right now. Now these are in your book on pages 671 and 672. These are the four basic formulas. We'll have those here in a second. There are a few more on another page. Oh, it's later on. Hold on. Here we go. On page 681. I'll remind you of that one again when I do section 10.2. On 681. You just have to know these. It's not that you can't derive these things if you need to, and I would like for you to be able to. The problem is it just takes a damn long, right? Like you can't, remember, this is just the translation step. After this, I have to solve a problem, and after that, I have to untranslate it. Yeah, so I need to be able to do this relatively quickly. Okay, so let's see what we have then. Okay, we're going to go ahead and make a table here, and we'll discuss some properties. I'll make a table over on the right because I want to use these a little bit. Okay, so let's go into function. Let's go to f of t and Laplace transform of f of t. Now what we've already done is we've already done e to the at, right? So I know that the Laplace transform of e to the at is 1 over s minus a. Fantastic. We've discussed we've utilized basically two other types of functions, basic trig functions, sine and cosine, and polynomial functions. So let's talk about polynomial terms. How about t to the n power? Okay, fair enough. The Laplace transform of t to the n power is n factorial divided by s to the n plus 1, yes? And hopefully we all remember what factorial is, yeah? Okay. If you don't, again, you can search for it online, or again, it's just the product of all those numbers down to 1, okay? All right, let's talk about, let's say, sine bt and cosine bt. Now these are similar. Normally they're almost the same. They're very, very similar. Sine bt, the Laplace transform is, stickiness on my board. Sorry, is b over s squared plus b squared, and for cosine bt, it's s over s squared plus b squared. Okay. All right. Okay. So for right now, these are the four we need. Again, there's a few more on page 681 or whatever it is. I said the second chart was on, and we'll maybe get to those. Okay. But right now, we just need to know this. Now, again, we can derive these formulas by going through that same limit process I showed you earlier, and you should try one or two of these. Just maybe just because. But you're going to need these. You're going to need to know these. You're going to need to memorize these. Okay. All right. So what can I do with this? Well, the first thing I want to notice, the first thing I want to point out is we defined our Laplace transform using an integral, didn't we? Specifically a definite integral, and a definite integral. Isn't it a linear transformation? Yeah. Which implies that it's both scalar invariant and additive, right? It's got those two properties. And it turns out these formulas, they have the same properties. So let me put this example up here. So 3t squared minus 5 times cosine 2t plus sine 3t. So let's take a Laplace transform of this. Now what I know, again, I get the properties of linearity here, right? So I know that it's additive, I know that it's scalar invariant, and we're actually going to try and apply those things right now, right? So here we go. So if I'm looking at the Laplace transform of f here, I don't have to write the Laplace transform of the whole thing, right? Because again, each individual term I can take a Laplace transform of, and each scalar can be factored out. So I can rewrite this as 3 times the Laplace transform of t squared minus 5 times the Laplace transform of cosine 2t plus the Laplace transform of sine 3t. Okay? And now you'll note that each of these things, it fits one of these formulas, right? Okay, see if we can apply these. So let's see. So I've got 3 times, okay, Laplace transform of t squared. Here we go. It's my polynomial term. That's t. N is 2, so it should be 2 factorial. Okay, 2 factorial over s to the 2 plus 1, which is 3. Okay, so minus 5 times. Here we go. Laplace transform cosine 2t. Here's cosine bt. 2 is b. That's s over s squared plus, well, b is 2 here, so 2 squared, that's 4. And then sine 3t, here we go, there's sine. So that's b is 3 here, so 3 over s squared plus 9. Okay, I'm going to clean this up a little bit, but I'm not going to do too much else with it for reasons I'm going to get to in a second. Okay, 2 factorial is 2. So this is 6 over s cubed minus 5s over s squared plus 4 plus 3 over s squared plus 9. I'm not going to combine these factors. I don't really want to unless I have to. And the reason is I may need to take them apart again later. Whenever we start doing full problems involving Laplace transforms, we'll have to make a determination as to whether or not we want to do either several small partial fraction decompositions or one larger partial fraction decomposition. I like doing one larger one, but I don't know, maybe you don't. You're gonna have to make a personal decision on that. Okay, and we'll get to some of those in a minute. But yeah, this is it. This is our Laplace transform, and these are not terrible, right? We may have to get a little bit creative on how to rewrite some of these things in terms of some polynomial sine or cosine. For example, right? How would you do cosine squared? Yeah? I hope you're all telling yourself right now, oh, the power reduction formula. Yeah, I remember that one from trigonometry. Nod. I can't see you nodding, but I'm trusting. Okay. How would you do hyperbolic cosine? Isn't hyperbolic cosine a sum of exponential functions, right? It's e to the 1/2 x, e to the x plus e to the negative x times 1/2. Yeah, whole thing times 1/2. Again, that just follows these rules, right? All right, as normal, there's going to be some practice problems. This section's not terribly difficult. The end result for this section is for you to be able to do this, right? Be able to translate this into Laplace transform notation very, very quickly, right? I kind of need these things to be second nature. We can't use too much time on these things. We'll have other... we'll have other things to occupy our time once we get to the larger versions of these problems, okay? All right, guys. As normal, there's homework. It's already been posted under announcements. Make sure you work those problems in the book. Again, if you have any other questions, email me. We'll do a lecture session on this maybe. I don't know, maybe next week, but we'll see. Okay? All right. Good luck.